Hello. Today, in this video, I'd like to talk to you about KSP and solubility. We're first going to take a look at what a solubility equilibrium actually is. We're then going to discuss the concept of molar solubility and do some example calculations. We're then going to finally do some calculations dealing with the common ion effect and precipitation. So first, let's take a look at what solubility actually is. So solubility equilibrium involves the equilibrium between the rates of two processes, dissolving, or ions going from a solid into solution, and then either recrystallizing or precipitation. You can use whatever word you'd like there, for those ions then coming back and reforming that solid. To show you an example, let's take a look at the compound Ag3ASO4, or silver arsenate. Imagining this process, it could dissolve, and when this compound dissolves, it's going to break up into 3 Ag plus smaller ions and an ASO4 ion, which is 3 minus, in solution. And so that's my process of dissolving. The backward process, though, can also happen at the same time, and we can have silver and arsenate coming together to form our silver arsenate back in the solid form. So a solubility equilibrium always involves this type of an equilibrium expression here. Now, we're going to say this is a solid, and both of these ions are implied to be aqueous. So like we've seen before, we could write an equilibrium constant expression for this reaction. And if we wrote that K value out, here it's going to be just Ag plus cubed times ASO4 3 minus. And on the bottom, we're not going to have anything because our only reactant here is a solid. And so what we give the name of this is a KSP. SP standing for solubility product, literally being that the only thing we have here are products and no reactants. So our KSP is just the equilibrium constant expression for a solubility product here. Now, let's take a look at some examples of different KSPs and talk about what a KSP actually means. And so to do that, I want to look at a series of different hydroxides. First one we're going to take a look at is barium hydroxide. And if you look back in your textbook, in Appendix C, you can see a table of solubility product constants, and they list the solubility constant for barium hydroxide as 5 times 10 to the minus third. Then if you look up calcium hydroxide, that compound is a solubility product constant of 5.5 times 10 to the minus sixth. And then finally, if you look up magnesium hydroxide, it's going to be 1.8 times 10 to the minus 11th. So what I want to talk about is what this is going to actually mean. The larger your KSP, if you have a high KSP, something like barium hydroxide, if this number is high, that means the amount of dissolved ions can also be really high. So the higher your KSP, the more soluble your salt is. And so if you look at this chart, we're going to say that solubility is going to increase as you go from magnesium to calcium to barium hydroxide. This, by the way, explains why we call barium and calcium hydroxide strong, but we don't consider magnesium hydroxide strong at all, because even though these are slightly insoluble, they have a fairly significant amount of ions that will dissolve in solution, whereas magnesium hydroxide barely dissolves at all. It's times 10 to the minus 11th, and so it doesn't count as a strong base, and so we would just consider it weakly basic. Just as a comparison, though, one of our big strong bases is NaOH, sodium hydroxide. And if you're curious, the KSP of sodium hydroxide is 110. It's greater than 1. It's larger than any of those KSPs. And so that's why we consider sodium hydroxide such a strong base, whereas all these other ones, they're strong, especially barium and calcium. We don't consider magnesium strong, but not quite as strong as sodium hydroxide would be because of the way that they dissolve in solution here. Molar solubility is the maximum amount of moles of a solid that can dissolve in a liter of solution. Essentially, it's like a molarity of the ions that are going to dissolve in that solution. So what we can do here is take a look and see, well, how do we figure out, given a KSP, what the amount of moles of a solid can dissolve in there? And just like we've seen with all our other equilibria, this is going to involve ice tables. Let's take a look at it for that barium hydroxide we saw. So if you take barium hydroxide, BaOH2 is going to be in equilibrium with Ba2 plus and 2OH minus, and these are both aqueous, and we have solid barium hydroxide. If we set up an ice table, now we can call X our molar solubility. It's the amount of this that will dissolve. So let's imagine we start with that maximum amount of barium hydroxide. That's all going to dissolve to form 0 barium hydroxide in solution. If we imagine that these two ions start at 0, this is going to go up some amount X. Because the 2 in front of our OH minus, that's going to go up an amount 2X. And so I'm left at the end with X and 2X of my barium and my hydroxide. We then can set up our KSP expression. KSP is going to be our barium times our OH minus squared. Then plugging in my numbers from equilibrium, I get that the KSP is equal to X times 2X squared. Now, on the previous slide, we had said that we know the KSP of barium hydroxide is 5 times 10 to the minus third. And so if I FOIL this out, or take that exponent and bring it down to both sides, I get 4x squared times x, or 4x cubed. Solving for x then, divide by 4, take the cube root now, it looks like I get an x of 0.107 molar. And so that represents the molar solubility of my barium hydroxide. 0.107 molar will be the max amount of moles of this solid that can dissolve in a liter of solution. Now let's go ahead and take a look at how the common ion effect can change the solubility constants that we have for a solution here. We're first going to take a look, though, at an example of how to calculate KSP given the molar solubility of salt. So what you do is go ahead and write out the solubility expression for our lead iodide. It's going to be a solid that's going to be in equilibrium with the ion Pb2 plus in 2 I minus. We then can go ahead and set up our ice table. And we know that that lead iodide, there's going to be some molar solubility X that will break up into to form 0 at equilibrium, where they're going to have these two ions start at 0. They're going to add X in 2X because we get 2 iodines for every lead to give us equilibrium concentrations of X and 2X. But wonderfully, we already know what X is. X is 1.21 times 10 to the minus third molar, our molar solubility. So when we write our KSP expression, it's going to be X times 2X squared. Just like we saw in the last example, we're going to get 4X cubed. So we can plug in X here, 4 times 1.21 times 10 to the minus third cubed. I get a KSP for our lead iodide of 7.1 times 10 to the minus 9th. So it's just like that problem we saw before, but backwards, and so that makes it a little easier. But now we want to think about, well, what's going to happen to the molar solubility if we already have some iodide in solution, and our source of iodide is going to be coming from NaI. This is a good electrolyte, so that's going to break up into Na plus and I minus. And so what we can do is set up our ice table again, but now we're going to have to change a few of our values. If we come down here, we're going to start with our lead iodide again as a solid, breaking up into lead 2 plus, into I minus. Initially, we're going to say that we still have some X amount of our lead iodide, 0 lead, but now this 0.1 molar is my initial concentration of my I minus. Then this is going to go down by an amount X to form 0. That's going to go up by an amount X to form X. And this is going to go up by an amount 2X to form 0.1 plus 2X. Now, if you look at our KSP at 7.1 times 10 to the minus 9th, we can still make the small x approximation here and say, hey, this 2x is going to be insignificant compared to that 0.1. That simplifies our calculations a lot, because then we can say the KSP is going to be equal to x times 0.1 squared. Solving for x here, we know our KSP from above, 7.1 times 10 to the minus 9th equals x times 0.1 squared. Solving that for x, I end up getting 7.1 times 10 to the minus 7th molar. Now, what I want you to look at is compare that molar solubility with our molar solubility from before. Before, we could get 1.21 times 10 to the minus 3rd molar to dissolve in solution. That's a lot larger than we could here. The reason why is because we have excess iodine in solution, and excess iodine causes this reaction to shift to the right, or sorry, shift to the left. It's going to shift away from our lead and our iodine, and because of that then, less of this is going to be able to dissolve. So it makes sense that my molar solubility here is much less than the molar solubility that we had before, and that's what the common ion effect does. Lastly, let's take a look and see how we can know whether something precipitates or not in one of these solubility equilibria. So our question we have for us here is, will a precipitate form when 10 mils of 0.050 molar lead nitrate is added to 500 milliliters of 0.1 sodium iodide? So here, what we are doing is we are adding a certain amount of lead 2 plus in solution and a certain amount of I minus into solution, recognizing that those two pieces are part of that equilibrium we had before. Our Pb2 plus, sorry, our Pbi2 going between Pb2 plus and 2I minus. So what we need to do is go ahead and calculate the concentrations of each of these solutions in our final solution, and then compare that to the KSP we had before. Now, when we mix these two things, we are going to have a dilution here. So if we take the case of our lead 2 plus, it initially starts out at a concentration of 0.050 molar. That's our M1. Our V1 is going to be the 10 mils that it starts off with, and it's then going to go to some M2 times, now I'm adding it to 500, so 510 mils. And so if I calculate the new concentration of my lead 2 plus after dilution, it looks like I end up getting 9.8 times 10 to the minus 4th molar. I'd have to do the same thing for my iodine here. My iodine, M1, is going to be 0.10 molar. It isn't 500 mils to start with. I don't know my M2 yet, but I know that my V2 was once again 510 mils, and so M2 for my iodine, when I calculate it out, is 0.098 molar. So those are my new concentrations, initially, of lead 2 plus and I minus in solution. Now, as we saw before, at equilibrium, the products, Pb2 plus times our I minus squared, are equal to KSP. But we don't know if this solution is at equilibrium. So let's go ahead and test that out by calculating a Q value. So we're going to say Q, that's our equilibrium expression not at equilibrium, is going to be the molarity of our lead, which is 9.8 times 10 to the minus 4th, times our I minus concentration, 0.098, and you can't forget to square it from here, and that's going to be my Q expression. If I go ahead and calculate out what Q is, I get 9.4 times 10 to the minus 6th, which we know from the back is greater than our KSP, because our KSP on the previous slide was 7.1 times 10 to the minus 9th. And so because our Q is greater than our KSP, that means we have too many ions in solution. There's more ions in solution than there should be predicted due to equilibrium. So anytime that the Q is greater than the KSP, we're going to form a precipitate. We have a solution that is oversaturated. Precipitate. To finish a chart off then, we know that Q equals KSP only at equilibrium. But I want to think about what kind of solution I've made if Q is less than KSP. If Q is less than KSP, I don't have as many ions in solution as I could, the maximum amount, at a full equilibrium, and so we're going to call that an unsaturated solution. Whereas a saturated solution is going to occur anytime I have an equilibrium here. So my equilibrium is saturated, and if I have Q equals KSP, whereas I'm unsaturated if I have a Q less than KSP. Okay, that's been a look at solubility equilibria. Thank you so much for watching. Have a great day.